Okay, guys. Little mini lesson on continuity, but I do want you to have now deeply ingrained in your head. This is the third time that we've talked about the definition of continuity. These 3 points, point 1, point 2, point 3, should now be committed to memory. So committed to memory that at any time, like maybe in the next hour class that we have, at any time I should be able to ask you for the definition of continuity, not just as a straight up definition, which of course you will be able to provide, but also as an application to why a point may or may not be continuous, or why a graph may not be continuous at a particular point. To be clear, to be continuous at x equals c, so what you look at in continuity at a point is you look at it at a location. The singular of location, I know location already is kind of singular, but the specific one is called a locus. Not a locust, but a locus. So the locus is x equals c. So you're focusing in on a particular x value as you scan left to right on a function. And you're trying to decide at that locus, is the graph continuous, or is the function continuous? Strictly speaking, continuity is a property of a function, not just of a graph, although a graph can be used as a visual aid to determine continuity. And I had the question earlier today as to if graphing is an acceptable means to determine that. Of course it is. You can always graph something. You just need to be able to explain mathematically what's happening here, which involves these 3 points. In any order, just raise your hand and tell me what you remember about these 3 points, because we've done these. Ryan?
Well, one thing is that f of c exists.
Okay. So we're going to call that number 2. F of c exists. Izzy?
The limit of x approaches c from the left is the same as the limit as x approaches c from the right.
Okay. Limit as x approaches c. Now, we've got to be very careful when we write this. I have to put of f of x, because the limit as x approaches c one way or the other in and of itself is just an operation. You're actually applying that operation to something. Sort of like saying sine without saying the sign of something. But the limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x. And this is another way of just saying that the limit exists, but this is a more specific way of saying it. Okay, raise your hand. Last point. Okay? Yeah, they equal each other. So what we say is the limit as x approaches c of f of x, something that we've established exists by the first condition, equals f of c. And for it to be continuous in a closed interval, in a closed, let's try to write the word closed. In a closed interval, this is true at every point. We'll say true for all c contained in A to B. That's saying in a closed interval, it's true for all possible locations contained in the closed interval. There is one minor exception to this that I want to verbally talk about that should make sense to you. It has to do with condition 1. In a closed interval, I would say that the graph and the function is continuous everywhere on that closed interval, including the endpoints, even though on the left endpoint there is no limit as you approach from the left, and on the right endpoint there's no limit as you approach from the right. It doesn't make sense to say that this is not continuous, because then that wouldn't be, then the one next to it wouldn't be, then the one next to it wouldn't be, then it's just the whole thing collapses. So it's okay to talk about the limit, the one-sided limit at an endpoint. We don't even consider a right-sided limit of a point where there is no right side. That's different from where there is a right side and it's approaching infinity or approaching a hole or something else. So we won't deal with that too much. I just want you to be somewhat aware of that. Okay. Now, you're going to get questions today that ask about where graphs and where functions are continuous. This is a very positive thing. Where is it continuous? Because in order to know where it is continuous, you must also know where it is not continuous. So where, come on, where is r of x equals, I'll give you an example, x minus 2 over x squared minus 6x plus 8. Where is this graph, this function, continuous? My freshlings are learning how to factor. They just had a factoring test, and now we're dealing with rational expressions, and they're learning what the zeros of the function are and what the domain restrictions are. And they're still trying to struggle bus between which one goes in the numerator and which one goes in the denominator. I know. You guys were there. You were there. It now should make perfect sense to you that a domain restriction creates a divide by zero problem. And a zero of the function itself creates a, well, not a divide by zero. But let's factor this. And can you guys tell me what is the zeros of, or what are the zeros of this function?
4 and 2.
Simba, that would cause you to divide by zero.
Oh, zeros.
None.
Yeah, there are none. This graph has a hole at the only place where it seems to cross the x-axis. Does it make sense to you that this graph would seem to cross the x-axis?
Yeah.
It would appear, and on any graphing utility that you graph this in, it would look like it crosses the x-axis, because graphing utilities don't give you holes unless they're the TI-84 and they graph pixels, and the pixels are so large that you can actually see the gap where it tried to graph the one pixel and it can't. That's one of the other advantages of the TI-84. You can see holes, and it's not a feature so much as a limitation that actually is kind of a feature, because you can see it seriously graphs like this. Like it graphs pixel, pixel, then it skips one, then pixel, pixel, and this is sort of where you can see the graph graphing. Like its pixels are so...
You can make it go from 1 pixel to like 3 pixels wide. I don't know why that's even a setting, but it is, and you can make it happen. And I don't know why people do it, but
yeah.
Apparently...
Your Inspires, the pixels are too small to see that, and so it's not going to calculate this. But in any case, this simplifies to r of x is equal to 1 over x minus 4. But I think you guys get enough of a point to know that this is not a true simplification unless you specify that x is not equal to 2. Now the two of these are the same. And it is not necessary to specify that x can't be 4, because we see that here and we see that here. And writing it again right here is redundant. But writing x is not equal to 2 here is not redundant, because you lost the information by canceling that factor out. This is a hole, a point of discontinuity. That represents, say it, asymptote, a vertical asymptote. That's a divide by zero that you cannot remove. We removed this, we didn't remove the x minus 4. Okay, now the reason I'm pointing this out is because we're going to graph it. And I sketched the graph in period 1. Because Potts was so specific about do I need graph paper, I'll just do a grid here and just annoy the crap out of the people who didn't do it. I don't really care. And then we're going to put a vertical asymptote, and since I now have a grid and I can precisely calculate 4 over instead of just putting an approximation, since I was so smart in getting graph paper out, I'm going to put a vertical asymptote down, and we're going to plot what we know about this. This is great review of rational functions. That's all I'm doing right now, is just kind of reviewing this. So you can see how to graph this. What's the shape of that? What's the general shape of 1 over x? Show me with your hands. Oh, dear God.
It's like this. It's like this. Whoa,
This is one of the graphs you guys should know. It does this. It's a hyperbola. It's a hyperbola that's tilted 45 degrees, but it's still a hyperbola.
Wait,
Okay. No.
please.
I also want to talk about limits to infinity, which is a topic we're going to hit up not next week, but right when we get back from Thanksgiving break, and we pull it from the other book, because this book it doesn't do it in enough detail. So we get to the other Precalc book and the other Calc book. But as I plug in a super large value of x, which is this graph never going to reach? 0. It's going to get really close, but it's never going to reach 0. And that's also going to happen with a super small value of x. We're going to get 1 over negative infinity, which is like negative 0, which is still 0. It's just 0 from the other side. So I get a graph that looks, we have horizontal asymptotes happening at the end. I typically try to draw asymptotes for horizontal things at the very end points. It doesn't matter so much in the middle, but it's like an attraction at the end. You get something that looks like this and this. But I'm going to sort of fix that sketch a little bit more, so don't worry. I'm going to delete this here in a second, because I can. And what's the y-intercept of this?
None. Oh wait.
Y-intercept.
0.
Negative 1/4. That's an actual point. Now, better question, where's the hole at? Hole at 2, comma, close with the 0, but not 0. Yeah, 2 at negative 1/2. The hole's at 2, but I'm going to plug 2 into the non-canceled version. And I get 1 over 2 minus 4, or negative 1/2. So I have a hole at 2, negative 1/2. That's appearing right here. and this gives me a sense of where it actually graphs. So now you have enough information to answer the question on what interval is this graph continuous. So tell me, continuous on, let's go left to right,
Negative infinity.
to, then,
2 to 4.
yep,
4 to infinity.
okay. This graph highlights the two different kinds of discontinuities that we typically see, points of discontinuity and vertical asymptotes. Let's answer a few questions about it while we have this. Yeah, Park?
Why did you talk about yesterday that the U should be replaced with commas?
It's a silly, silly little argument. It's a really, really a silly one. I think I talked about it in period 1, but not in period 7. Or period 2, not period 7. It has to do with, there's an argument on math blogs, which is a thing, that if I'm saying it's continuous, then I'm describing that I should be able to draw and connect all of this, whereas the U means that it's all one complete set instead of disjointed sets. I'm not going to worry about that. But it's a silly little thing.
Do you have your own math blog?
No, I don't, Simba. The limit as x approaches 2 from the right of r of x. The limit as x approaches 4 from the right of r of x. Then we're going to do the limit as x approaches 2 of r of x. And the limit as x approaches 4 of r of x. I wanted to just get an answer for each of these 4. What would you say for the limit as x approaches 2 from the right?
That is infinite. Oh wait.
It's right here. We're approaching x equals 2 from the right. That's that circle, that's negative 1/2. What about 4 from the right? That's going to be positive infinity. 2 neither from the right or from the left, which means from the right and from the left. Negative 1/2. The limit is the same from the left to the right. 4?
Does not exist. Oh, Mr. Payne-Elliott?
Yeah.
I'm confused because we keep talking about how infinity sometimes works for when a certain question is asked and infinity doesn't work.
We're going to use infinity if we're talking about a one-sided limit. So we're never going to say does not exist for a one-sided limit. We'll always be able to describe it somehow. And also, if I have a limit look like this, where it's approaching a vertical asymptote from the same side or from the same direction, we'll describe it as positive infinity, just to distinguish it from the case where they split. Okay? The only time we'll say does not exist is if we're describing a two-sided limit where they approach differently. But it's still just a description. Okay, number 2. F of x equals x squared when x is less than or equal to 0, x plus 1 whenever 0 is less than x is less than 2, and 5 minus x whenever 2 is less than or equal to x, which is less than or equal to 5. And I want you to determine where f of x is continuous. Okay, let's start with looking at the one-sided limits, because that's really where we need to examine. I need to examine the points at which the graph changes from one piece to another piece. So I want to look at the limit as x approaches 0 from the left of f of x, and I want to look at the limit as x approaches 0 from the right of f of x. What is the limit as x approaches 0 from the left?
0.
Yeah. As I approach from the left, I'm looking at this curve here. That is approaching from the left whenever x is less than 0. And the value would be 0 squared, or 0. Now let's approach from the right. As you approach from the right, what's the limit? 1. That would be 0 plus 1, or 1. that refers to this region here. It does not matter that the equals was on the first one and not the second. It really didn't even matter where the equals was. What Carlos pointed out this morning, which he's absolutely right, is that it does matter that there is an equals, because if there wasn't an equals on at least one of them, it would still be discontinuous at that point, regardless of if it converges, because it's still the function value wouldn't exist. Remember, that's the second condition, is that the function value exists. Now, it's also very improper function notation for the equals to be on both of them, because if they're not the same point, then it's not a function, right? So, okay, back to this. We know that it's discontinuous at 0. Let's look at 2. Is the limit as x approaches 2 of f of x the same from the left and from the right? Yeah. 2 plus 1 is the same as 5 minus 2, which is the same as 3. The limit's the same for both of them. So the intervals that we say it's continuous on, f of x is continuous on negative infinity to what?
To 0.
Then from 0 to...
2. Right?
Nope, we're okay at 2. We just showed that the left side limit, so it's just 2 to 0 to infinity. 2 is good. We can skip right over that. Okay.